Okay, so let's jump in and start working on our first example then. All right, so for this example, we've got a rod assembly. Okay, it consists of a steel rod, a brass rod, and a copper rod all connected together somehow. And all of these three different materials, the material properties are given for us for each one. So we've got a modulus of elasticity, a coefficient of thermal expansion for each material, the E and the alpha for each one, and then the area of each of these rods is also already given to us as well as the length of each segment. All right, so the problem statement says if the temperature is changed from 12 degrees Celsius to 18 degrees Celsius, determine the force exerted on the supports. Okay, so let's just go ahead and obviously think about this. So we've got a temperature change that's going from 12 to 18. All right, so our temperature change, delta T, is a positive 6 degrees Celsius, right? So it's positive. The delta T is positive, meaning that our rods or our bars here are going to want to expand. And if our rods are wanting to expand, but they can't, right, because they are being supported at each end, wanting to expand and they can't, that means that the reactions then that are developed are going to be compressive reactions. So they're going to push on the rod assembly, like we've drawn just now. Let's just take a second to think about this though too. What if I were to cut a section in the middle? What if I wanted to know what the internal force was in each of these three different rod segments? If you can imagine a free body diagram of any of these, let's just look at the left free body diagram. Maybe we'll call this, it doesn't matter what we call it. Just starting at the left, we've got some reaction, right? Then we've got our first cut, the first cut within the steel segment, right? The internal force that's developed within the steel is going to be equal to the reaction, correct? And if you do the same thing for the other two free body diagrams, what you find is that the P, the internal force, the internal axial force P for all three segments is just going to be whatever reaction force is developed, right? So no matter where you cut your free body diagram, the only force that's going to act on that free body diagram is this reaction, and thus the internal force must also equal that reaction. Okay, so we don't have to worry about finding different P's for each segment. All we're worried about is figuring out what the reaction is, but we know that it will also be equal to P. Okay, so just keep this in mind, that the reaction force that is developed will also be the internal force in all three of the segments. So those are just kind of our two initial setup things that we need to know, that we should be able to notice just from looking at the problem statement and the diagram. Okay. Our first legitimate step then is to calculate thermal deflections, because what we're going to do in our minds is we're going to remove one of the supports and allow this assembly to expand unrestrained, and we need to calculate that expansion. And we know that the thermal deflection of the entire assembly is just going to be the mathematical summation of each individual segment, right? So delta T total is equal to the delta T from the steel plus the delta T from the brass plus the delta T from the copper, right? So we know our equations. Alpha, delta T is equal to alpha times delta T times L. So if we do plug that in, the delta T total, the delta T is the same for all three segments. So I'm going to go ahead and factor that out of our equation. And we're going to have delta T times alpha steel, length of steel, plus alpha brass, length of brass, plus alpha copper, length of copper. And if we just plug and chug here, we get 6 degrees Celsius times alpha T, which is 12 times 10 to the negative 6, times the length of steel, which is 300 millimeters, plus alpha brass, which is 21, times 10 to the negative 6, times the length of brass, which is 200. And you add in alpha copper, 17, times 10 to the negative 6, times 100 millimeters for that one. And so we get in that bracket there. And so what we find out then is that the total deflection, if this thing was unrestrained and allowed to expand the way it wants to, the entire thermal deflection would come out to be 0.057 millimeters. Okay? So the next step in this problem then is to figure out how much load it would take if we have removed that support. How much load would it take to push that assembly back and compress that assembly back to where the total deflection is 0? And again, we'll just call this the force deflection, step 2. And we know from our previous sections that we've worked with on axial members that the total delta of an assembly is just equal to the summations of each individual one. So let's say delta, and I'm going to call it delta R from delta reaction, right, is equal to delta steel plus delta brass plus delta of copper, okay? And if we're working with force deflections on an axial member, we know that our equation is PL over AE. And also, again, just like the thermal deflection, the P force that's going to be in all of these equations is going to be constant, right? We determined that from our free body diagrams that we first drew. And that P force is also going to be equal to the reaction force that's developed at both of the reactions. So I'm just going to then pull out that R force, which is the reaction, pull that out of our equation, and so that what we get is it's the length of steel over A steel, E steel, plus the length of the brass divided by A brass, E brass, plus the length of copper divided by area copper times E copper, and all of that. So if we start plugging and chugging into this equation, what we find, and we'll just put it in there. The steel is 300 millimeters. The area is 200 millimeters. And the modulus of elasticity is 200 gigapascals, which is 200 times 10 to the 9th. But since I'm already working in millimeters, what we can do is just say that E is equal to 200, and by doing so, our reaction will come out in kilonewtons instead of newtons as the base units. So let's just continue this format then for the brass and the copper. The brass has a length of 200 millimeters. The area of the brass is 450 millimeters squared, and E for brass is 100 gigapascals, but we'll drop the 10 to the 9th so the units work out. And then finally, for the copper, has a length of 100, an area of 515, and a modulus of 120 gigapascals. So if we run this math out, what we end up with is, just in math terms, is 0.01356 times R. And this equation, this 0.01356, is dependent upon all of our length measurements being in millimeters and all of our force measurements being in kilonewtons. So now all we have to do is solve the system, and we know that the thermal deflections, how much it expanded thermally, is 0.057 millimeters, and that we know that the force deflection would be 0.01356 times R, with R being in kilonewtons. We know those two deflections need to be the same, right? How much force is needed to compress this rod assembly back down to where the original length is, or where the deflected length is the original length. So we just set this equal to each other. So we say 0.057 millimeters is equal to 0.01356 R. And if we do this math, R comes out to be 4.2. And since we need this to be out in kilonewtons for our units to work out, that's what it is in. So the reaction that is developed on both ends is 4.2 kilonewtons, right? 4.2 here, 4.2 here. And if you were to make a free body diagram cut at all of those, you would still have 4.2 kilonewtons within each one of those three rods. All right. So that's our first example on restrained thermal expansions. Let's take a look at a second example. So we've got we're looking at some train tracks, right? We're looking at them from like a side view, if you will. The temperature of this steel railroad track, right? So that means we need alpha of steel, is increased from negative 20 degrees Fahrenheit to 90 degrees. What is the required gap between the rails so that they just touch at the maximum temperature, right? So how much gap do we need just so that when the temperature goes from negative 20 to 90, so that the gap closes, all right? What if, though, the next part of this question, what if the temperature were to rise to 110 degrees Fahrenheit? What would be the stress in the rails? All right, so the train track rails, they have an area of 5.1 square inches. Alpha of steel is still 6.6 times 10 to the negative 6. And E for steel is 29,000 KSI. Okay. So what is, from the problem statement that's given, what can we say? First, we know that the temperature is changing from negative 20 to 90. So that means our delta T then is a positive 110 degrees Fahrenheit. And we need to know what the gap is so that the gaps will be closed at this 110 degree delta T. So let's just start working with our equation. We'll say step 1 is gap. As we're going to determine what our gap needs to be. Does it make sense that if these railroad tracks were all laid side by side, they were all 40 feet long, or end to end, I guess, they were all laid end to end and the gaps between them were delta, does it not make sense then that each one of them are going to expand half of delta to the left and half of delta to the right, such that the total delta is just delta as shown in the diagram? All right, so if that all makes sense to you, then what we need to know then is that the gap, the actual delta, right, the delta gap is going to be equal to alpha delta T times L. which alpha is 6.6 times 10 to the negative 6. Delta T is 110 degrees Fahrenheit. So that's the thermal strain. And then the original length is 40 feet. I'm going to go ahead and put 40 feet times 12 to go ahead and convert our answer to inches. So if we run this math out, what we find is the gap needs to be 0.348 inches, so that when the rails undergo a temperature change of 110 degrees, the rails will close the gap. All right. Next part of this equation, of this problem, though, it says, what if the temperature were to raise to 110 degrees? What would be the stress in the rails? So at this point, the first 110 degree delta T, going from negative 20 to 90, that was basically unrestrained thermal expansion, correct? Like, there's nothing compressing it. There's nothing to react or withstand or to stop that rail from expanding. But now that you've closed the gap, there's the adjacent rails now are going to withstand that expansion, correct? So now we've got restrained thermal expansion. So let's make that our step 2. Restrained thermal expansion. We know that delta T is equal to alpha times delta T times L. Alpha still 6.6 times 10 to the negative 6. Delta T this time, let's look at just the restrained portion, right? How much would this rail expand if it were restrained from the point it is restrained to the point that we're looking at, right? So we're looking from 90 to 110 degrees Fahrenheit, because at 90 degrees Fahrenheit the gap is closed. But what if we were to increase it to 110, right? So our delta T in this portion of our equation, we're only looking at 20 degrees Fahrenheit. And then the original length is still 40 feet. So that's 480 inches. All right, so let's work this math out. I haven't actually done this math yet, so let me take a second to do it. 6.6 times 10 to the negative 6 times 20 times 480 inches. We get 0.06336, all right, inches. We know that our reaction force, if we were to draw a free body diagram of this rail, the reaction forces at each end of the rail would still just be, they would be the same, but opposite directions. They would be compressing the rail. The magnitudes of those reactions will be the same, and we also know that the internal force within that rail will just be equal to the reaction force. So the PL over AE, for that equation, the P is just the reaction force. So again, delta R from the reaction force is R times L over AE. We know R is just R, that's what we're looking for. The length is 480 inches. Let's do it all in inches so our units come out correct. The area of the rail is 5.1 square inches. And our modulus is 29,000 KSI, right? So that is in kips per square inches. So that means if we work with this, then our reaction will come out in kips. So if I do this math, we got 480 divided by 5.1 divided by 29,000. We get 0.003245 times R. And if R is in kips, our units will work out. So we set these two values equal to each other, and we solve for R. So we take 0.06336 divided by our 0.003245, and we get 19.52 kips. Right? So that is the force, that's the reaction at each end of the rail. But the problem wants to know what would be the stress in the rail. So now we can just figure out the stress in the rail just by using our simple P over A equation. So we think step 3 can be stress. Sigma equals P over A. We know P is 19.52 kips. We know A was 5.1 square inches. So 19.52 divided by 5.1 gives us 3.83. And that's in kips per square inches, so KSI. So that is the answer for this example. So we go the first 110 degrees Fahrenheit from -20 to 90. We close the gap. We know that the gap needs to be 0.348 inches. But then if we take it another 20 degrees further to 110 degrees Fahrenheit, that will be restrained thermal expansion. And we calculated that at 20 degrees, at an additional 20 degrees Fahrenheit, the reaction that's developed within the rail is just over 19,000 pounds. And from that, we know that the stress in the rail, because since we know the area of the rail, comes out to be 3.83 KSI. All right. So let's move on then to our last example on thermal effects. This time it's just a little bit different. So what we've been given is a pipe assembly that's got fluid flowing through it from left to right, as shown by the arrows, right? That's the flow direction of this gas, or it's gas flowing. All right, so the pipe has an inner radius of 0.5 and a wall thickness of 0.2. If the gas flowing through the pipe changes the temperature of the pipe uniformly from where the temperature at point A is 200 degrees Fahrenheit to where the temperature at point B is 60 degrees Fahrenheit, determine the axial force that it exerts on the wall. Okay? The next sentence is crucial. The pipe was fitted between the walls when the temperature was 60 degrees Fahrenheit. So this pipe was installed at a temperature of 60, but the gas that's flowing through it has made the temperature at point A to be 200 and the temperature at point B to still be 60. So what we need to know then is delta at A is equal to 140 degrees Fahrenheit. Does that make sense? Point A was originally 60 degrees Fahrenheit, but now point A is 200 degrees Fahrenheit. At point B, I'm sorry, I need to distinguish this. This is delta T at A and delta T at point B. Point B was originally 60 degrees because that's the temperature it was fitted in. And now point B is still 60 degrees. So our delta T at point B is still 0 degrees Fahrenheit. But if delta T at point A is 140 and delta T at point B is 0, that means that delta T becomes a function of the length of the pipe, correct? So what if I was to then, we're just going to say X starts here at the left side and works our way to the right. So at X equal to 0, delta T is 140, and at X equal to L, which is 8 feet, delta T goes to 0. So if I need to know, then I need to figure out an equation for delta T. And I'm going to label it as delta T of X. Well, the change in delta T goes from 40 to 0 over 8 feet. So the slope, if you will, of the line that we're working with is negative 140 over 8 times X plus an initial value of 140. So that is coming up with an equation for delta t. When x is equal to 0, as in this equation, delta t is equal to 140, which is what we know. And if delta t, or when x is equal to 8 feet, our delta t comes out to be 0 from the equation, which is also what we know from the information that was given. This problem is just slightly different because since delta t is a function of x, we can't just simply take alpha times delta t times L. Instead, we need to integrate, correct? So this time, instead of it being, I'm going to say, delta t is equal to alpha times delta t times L. That's not going to work for this particular equation because delta t is a function of x. So what we're going to come up with is that delta t is an integral from 0 to L of alpha delta t with respect to x. Okay, this is the equation that we must use this time. And so if we know this, then it's just a plug and chug, right? Because we've got all the variables that we need. So delta t is equal to the integral from 0 to L. We know L in this particular case is 8 feet. Alpha is 9.6 times 10 to the negative 6. And delta t is negative 140 over 8x plus 140. All of this times dx. So if we do this, this is 9.6 times 10 to the negative 6. We can pull that out of the integral. We can do negative 140 x squared over 16. I'm sorry guys, I have messed up. I'm looking at my notes now. Let's fix this real quick before we get too far. Our delta t of x is in, let's just change it to where it's in inches. All right, so our delta t of x, it changes from 140 to 0 over 8 feet. Let's just change that 8 feet to 96 inches, okay? And then same thing, now that we're doing our integral, let's take our integral from 0 to 8 feet, but our 8 feet is 96 inches. We're just going to do all this so that our units come out correctly. So we'll change it here as well inside the integral to where it's negative 140 over 96x. And now we're good to go over here. So now we're back at our integral. We get negative 140 over x squared divided by 192 plus 140x. Evaluate that integral from 0 to 96. I hope I did not confuse anybody with this part of the equation. So you just evaluate this integral then, and we know that if this machine, or if this pipe were unrestrained, we removed one of the supports and allowed it to expand, we know that the delta t would be equal to 0.06 4512 inches. All right. And again, same thing where the reactions are going to be the same at each end because there are no applied forces to this pipe. So if you draw a free body diagram of it, there's only going to be 2 compressive reaction forces at each end at point A and point B, and that the P function then, that the internal force that is developed within the pipe is going to be constant along the length of the pipe and just equal the reaction. So again, all we have to do here is set delta T equal to PL over AE. We're solving for P, all right? That's what we're trying to figure out. Length is 96 inches. The area of the pipe is pi over 4 times the outer diameter, which is 1.4 inches squared, minus the inner diameter squared, which is just 1.0 squared. So that's the area. And then that's all in inches, and we know the modulus elasticity of this pipe is 15,000 KSI, so we say times 15,000 KSI. If we work all this math out, then we figure out that P is equal to R, and it's going to come out in kips, so P equals 7.6 kips. All right. And now that we know what the reaction force at points A and B are, there's 7.6 kips acting to where the pipe will be in compression. Once you know this, you know the area of the pipe. You could also calculate stress on the pipe. You could calculate a lot of things now that the reactions are known. All right. So that's all we're going to cover on the thermal expansion or thermal effects of axial members. Okay. Basically, the deformation of the equation of compatibility, right, is basically going to be that the total length of the pipe or the rod or whatever it is, it can't change. That's pretty well what it's going to be every time, to where you calculate the thermal expansion of how much it would expand if it were unrestrained, and then calculate the required reaction to compress or expand, it could be the other way, to the required force to bring that rod back to its original length, so that the total delta T is 0. All right. So I hope I haven't confused any of you guys with this. If you have any questions about it, please feel free to send me an email or text or anything asking any questions about it. And hope you guys have a good rest of your day. See you.